Good afternoon. And last class we have discussed the flocculation concepts. Okay, so after destabilization of the colloids, okay, after addition of the coagulants, and the particles are now you have to enhance the process to collide. Okay, so that you can have it up in the flocculation basin where you can provide or have some sort of a simple mixing. The particles may meet each other or collide each other, which will form a floc. Okay, and based on the classification, then the flocculation is being divided into or classified into two different approaches. Number one, macro flocculation. Number two, which is microflocculation, or otherwise orthokinetic and perikinetic flocculation. That's what we discussed in the last class. Okay, and different types of flocculator, and based on the mechanical mixing, you have mechanical mixing devices, and based on the channel, you have a horizontal flow and also vertical flow. So that's what we discussed in the last class. Okay, that covers the basic concept in flocculation. And we have also discussed last class with how to calculate the velocity gradient in the baffled basins and how to calculate the power requirement in the case of mechanical mixtures by introducing some formulas. Okay, so we'll see some numerical solutions now in the class. The first statement or problem statement in a baffled basin. So it is mentioned clearly in a basin, baffled basin, so that you could recall the basin. Okay, this could be the plan, or if it is something like on in a section, this is plan, this is in section, or okay, so this is your plan, maybe horizontal, and this is move up and down. This is about your vertical movement. Okay, so baffled basins, the detention time is 25 minutes, and it is being asked to calculate the head loss if the G value, velocity gradient, is 30 per second, 30 per second. And the temperature is 15 degrees Celsius. And you can refer the water chart or water characteristics table column. For 15 degrees Celsius, the dynamic viscosity as 0.00113 Newton second per meter square. Okay, so that's the value is being given. So you can directly substitute in this equation. These problems are not challenging. Okay, so G value we are already familiar. Square root of gamma Q H divided by mu into V. Okay, so it is also been rearranged like this: gamma H divided by mu by V by Q. Okay, V by Q. So it is also been related as T. Okay, so that's what the equation has been changed to. G is equal to gamma H mu into T, and you can take a square. G square is equal to gamma into H divided by mu into T. Okay, so where you can remember this equation, and based on the problem requirement, you can also slightly alter the formula. So here it has been asked to calculate the head loss value. So now you can rearrange the head loss equation. H is equal to G square mu into T divided by the specific weight of water. So G value is given in the problem as 30 per second, that is square, into the dynamic viscosity of water at a particular temperature, 0.00113 Newton second per meter square, into 25 minutes is being mentioned in the problem. So if you 25 minutes is being mentioned, okay, 25 minutes. So here it is in terms of seconds. So now we have to also substitute in the same units, 25 into 60 for the conversion, divided by 9810. That's the specific weight of water. So therefore you can calculate head loss in the baffled basin as 0.1554 meter. Is it okay?
Yes, sir.
Okay, so these are not very challenging. Please refer the the formula, and you can resubstitute. Okay, so there's a scope to find out the G value. You can find out. Okay, head loss value you can find out, or you can also in a position to calculate T value. So we are not solving in all combinations, but you just remember these are the ways you can solve the problem by using this formula. G value for a particular conditions you can calculate, head loss in a way solved, and you can also find out for a particular G value and other dimensions of the tank. You can also able to find out what is the detention time. Is it okay?
Yes, sir.
Okay. The second problem here also again a baffled flocculation basin is divided into 16 channels by 15 around the end baffles. Okay, so now you could able to understand better. Okay, this is 16 channels, 1, 2, 3, 4, then 15 around. Okay, it is something like this, 15 around end baffles. Okay, imagine now the situation is like this. Okay, okay. So 1, 2, 3, 4, 6. So it may have 16 channels. The channel is meant for this space, and this 15 around the end baffles. Okay, so it has been given like this, and total head loss, neglecting the channel friction, is being mentioned as 0.3 meter. It is also been mentioned like that, and the flow rate into the channel is 0.34 meter cube per second. Now you have to calculate all the individual parameters. Number one, power dissipated. Number two, the mean velocity gradient G value at 15 degrees Celsius with the basin dimensions of 4.88 meter deep, 4.57 meter wide, and 24.38 meter long. And you are also in a position to calculate G multiplied by T, GT value as a numerical value, because G per second and T is also again second will go off. GT is a value. Okay, GT is a dimensions as number. And if the detention time is 20 minutes, and you can also calculate what is the loading rate in terms of meter cube per day per meter cube of your baffle flocculation volume. Okay, so this data is rightly given. You can calculate one by one. Okay, yes. So power input, you can calculate this formula. You're already familiar in fluid mechanics, gamma QH. That P is equal to this specific weight of water 9810. Q, it is already been mentioned in the problem as 0.34 meter cube per second multiplied by 0.3 meter as a total head loss. So thereby you make it P is equal to 1000 Newton meter per second. Is it okay? So this is direct substitutions. You can calculate the power input. Is it fine?
Yes, sir.
Yeah. Then G value you can calculate by using this formula. G is equal to square root of P by mu into V. So that this also we are already familiar with this formula. And G, okay, so it is being asked to calculate the G value, and temperature has been mentioned, and you can refer the standard chart of water characteristics, 15 degrees Celsius. What is the dynamic viscosity of water? 0.00113 Newton second per meter square. Substitute in this equation directly. So P from the first step, and this mu at a particular temperature, 15 degrees Celsius, and V is equal to the volume of the basin. So standard dimensions of the basin has been given, that length, breadth, and also width. So thereby you can calculate the total volume. And by substituting in this equation, you may get G value as 40 per second. Is it okay? The second step, this also is not very challenging. That only the substitution of values with the wise manner. Is it okay?
Yes, sir.
Yeah, G value. And GT is very simple. G multiplied by G multiplied by T value, detention time. So G we have calculated in the previous step. Detention time, it is mentioned in the problem as 20 minutes. Then you just multiply by 60 to the conversion for again second. So if you multiply G and T, you may get 48,432 as a dimensionless number. Okay, so this minutes and both are in seconds. Second will go off. Thereby GT becomes 48,432. Okay, yeah. Now the loading rate, we are already familiar with the formula. The loading rate is equal to Q by volume, total flow divided by volume of the reactor. And Q, it is already been mentioned in terms of meter cube per second. It is already given in the problem. Convert in terms of meter cube per day. And volume, length, breadth, and width of the tank, we already calculated in the previous step. And Q by V will give you the value of loading rate in terms of meter cube per day per meter cube of your reactor volume. Is it okay?
Yes, sir.
Okay, so these are not very challenging, but these individual calculations or parameters are important in design. Okay, yes. Now we'll see one more problem. Flocculator, it is 4.88 meter deep, 12.2 meter wide, 24.4 meter long. So the flow of the water treatment plant is 0.566 meter cube per second. Rotating paddles are supported parallel to 4 horizontal shafts, and the rotating speed is 2 RPM. The center line of the paddle is 1.68 meter from the shaft. That means it's the mid depth of the basin, and each shaft is equipped with 6 paddles, and each paddle blade is 25 meter wide and 11.6 meter long. Assume the mean velocity of water is equal to 28% of the velocity of the paddles, and drag coefficient is 1.9 and estimate these parameters. Okay, so this baffle inside the tank, this also we discussed: horizontal flow paddle flocculator and vertical flow paddle flocculator. Also we have seen in the last class with the diagrams. Okay, so just refer and you could able to understand the problem statement. Okay, so You have a mid shaft and width. Okay, this could mid I cannot able to draw because you can imagine like perpendicular to the screen what you are seeing, and these are the boards. Okay, this is what we have discussed in the last class. Okay, so this may be kept inside along that the with a particular dimensions. That's what I told you. These paddles may be designed and mechanically fabricated and brought to the treatment plant, and you can place it inside the tank to have mixing. Okay, so read the statement, the problem statement in a clarity way. That way you could be able to identify each parameters or each values. So here now you have to identify or find out the difference in velocity between paddle and also water. That is number one. Velocity difference you have to find out. Power input, energy consumption, retention time, G value and GT value, and loading rate of the flocculator. So this is something almost 60 to 70% of the problem what we have seen in the previous one. Okay, yeah. So now velocity of the paddle. Okay, so you can use this formula. This also we discussed in the last class. Vp is equal to 2 pi Rn by 60. So velocity is equal to 2 pi R. That is 1.68. I think it is also been mentioned in the problem as 1.68 meter. The center line of the paddle is 1.68 meter from the shaft. Okay, 1.68 meter from the shaft. Okay, so 1.68 meter. So you can substitute 1.68 meter, and the number of rotations is also been mentioned like 2 RPM. You can substitute as 2 divided by 60, and you may get 0.3517 meter per second. Okay. So now the velocity that is also been mentioned, mean velocity of the water, which is 28% of velocity of the paddle. Okay, so now you can say velocity of the water is equal to 1 minus 28%, that is 0.28 into 0.3517. Thereby the velocity of the water you can calculate as 0.253 meter per second. Is it okay? This step is something is important. Just see that. Is it fine?
Yes, sir.
Okay, velocity of the paddle and that velocity of the water also you can calculate. Okay, yeah. Now you can find out the power. Okay, for that you can use this formula. This also we are discussed in the last class. Power is equal to CDA rho Vp cube, or velocity of the paddle cube, divided by 2. Okay, so now the area of the paddle you have to calculate. AP you have to calculate. So area is equal to that it is being mentioned in the problem as 4 shaft. Okay, it is mentioned in the problem as it is supported to 4 horizontal shaft, that is 4. Okay, that is 4, and each shaft consists of 6 parts. Okay, 6 parts like this. Okay, 6 parts like this. 6 parts like this. Okay, so thereby the total becomes now that is 4 into 6, and the bore dimensions is also being mentioned as 11.6 meter length and 25 meter width. That is also been mentioned in the problem. Thereby you can calculate the area. Okay, 4 shaft, and each shaft consists of 6 boards or 6 pads, and with the 6 pad length of 11.6 meter multiplied by 0.25 meter as a width. Okay, thereby total area becomes 69.6 meter. Is it okay?
Yes, sir.
Okay, so once the area is known, and all others are direct calculation, because CD value is mentioned in the problem as 1.9, and area of the paddle we have calculated 69.6, rho 1000 kg per meter cube, and this V is the relative velocity of the water, that is 0.253, that what you have calculated in the previous step, divided by 2, then you may get 1070.76 Newton per second, and you can convert in terms of horsepower, and 1 HP is equal to 746 watts. Then you can convert into that 1.435 HP, or you can also inform in terms of kilowatts. Multiply by 0.746, you may get 1.07 kilowatts of power. Okay, yeah. And the energy consumption now, the energy consumption is equal to the total power supplied divided by the flow rate. So that you can calculate directly. 1.07, what you calculated in the previous step, divided by 0.566 meter cube per second. So thereby the energy consumption is equal to per meter cube of volume, you have to supply 1.89 kilowatt of power per second. Is it okay? Kilowatt second per meter cube. Is it okay? This is also something is important. Energy consumption. Is it fine?
Yeah.
Yeah. Then detention time, that is very simple, V by Q. T is equal to V by Q. So V you can calculate, volume is equal to 4.88 by 12.2 into 24.4. You may get a volume as this. Volume divided by rate of flow, you may get in terms of second, 2566.57 seconds. You can convert in terms of minutes. So time of flocculation as 42.77 minutes. This also is not very, and once T value is known, and you can calculate G and GT value. So G value we are already familiar. G is equal to square root of P by mu into V. Okay, so P we have already calculated 1.07 kilowatts or 1070 divided by mu as 15 degrees Celsius 0.113 into volume as we have calculated in the previous step, that is 1452 square root. So G becomes now 25.53 seconds. Okay, and if you multiply with the time of flocculation, it is time of flocculation in terms of minutes, and I'm converting in terms of seconds. For that, multiply by 60. Therefore, GT value becomes now 65,550. Is it okay?
Yes, sir.
Yeah. And last one is about loading rate. That is also similar with the previous problem. That is Q by V. So Q, this is mentioned as 0.566 meter cube per second. Convert in terms of meter cube per day divided by the volume of the reactor or the baffle basin is 1452. And if you calculate, the loading rate becomes now 33.66 meter cube per day per meter cube of your reactor volume. Is it okay? So these are not very challenging problems, but the problem statement, you just look it or read it very carefully and use the appropriate equations to calculate the relevant parameters. Is it okay?
Yes, sir.
Yeah. So this covers your the flocculation altogether. So what we are seeing in the last class as a theory and some concepts, and the formulas are design equations to calculate the individual items, and whatever we are seeing today, it is about how to calculate the individual parameters.